bisectors. And bisecting is to cut in half. And so you get two equal parts. And a perpendicular bisector is a special bisector because it bisects and it hits at a 90-degree angle. So if you have a regular bisector, this angle can be any measure. And if you have a perpendicular bisector, you have a 90-degree angle. And in both, you end up with two equal halves. So our perpendicular bisector theorem says that if we have a segment, let's just call it AB for convenience, and we come in and we have a perpendicular bisector. That's not perpendicular. There. We have a perpendicular bisector, so we're cut in half. And we pick any point anywhere on this bisector. It can be up top here, it can be down here, anywhere at all. But if we pick some point on the bisector, then that point is going to be equally distant to both A and B. So if we do that, I can come in and go from A to C or C to B, and it'll be the same length. Okay. What this creates is, as you can see, it creates an isosceles triangle. Questions about that?
Know what big side angles are?
No, we're not doing any of that anymore. This is just saying that if you know that this line here is perpendicular and these two are the same length, then these two are going to be the same length. That's all that's telling me. Okay, so the converse of the perpendicular bisector theorem, it tells us the opposite. So if we have a segment and we have some point, and this point can be anywhere above or below, or even on the segment. See right here in the middle. So if we have some point and it's equally distant from the two ends of the segment, if you were to draw a line between that and the segment, it's going to be a perpendicular bisector. So this tells us how to find the perpendicular bisector. So that would make this perpendicular and those two the same length. So basically, what you have is you have a picture like this, where this is a perpendicular line. That's going to tell us that these two parts are the same length and these two parts are the same length. Whether we're using the original theorem, which starts with a perpendicular bisector and gives us equal lengths, or we start with equal lengths to give us the perpendicular bisector. And what we have is, if we look at this picture for triangle ABD, and BC and CD are labeled as the same length, that means that these two are also the same length. So if this is 4.1, this is also 4.1. Okay. Here, if we look at XYZ, these are the same length, which tells me that these are the same length. So if this is 3, then this is also 3. See that? And then you get some algebra. These two are the same length, QT and TS, which tells me that these two are the same length. And this one you actually have to do some work on to find X first, and then I should have fixed my typo. RS, not RT. So first I need to find X. I'm going to set these two things equal to each other. Okay. Subtract 2x from both sides. And you get 2x minus 7 is equal to 3.
Add 7.
So 2x equals 10. Divide by 2. And x equals 5. Okay, so that's halfway done. We wanted to find our s. Our s is 4x minus 7, so I'm going to plug that 5 in. So 4 times 5 minus 7.
Does it matter which of the two you use?
No, because they're the same length.
Yeah.
I'm just using rs because that's what I said to find. But
Yeah.
yeah, you could use the 2x plus 3 if you wanted because they're the same length, right?
Mm-hmm.
So it doesn't really matter which one. So I have 20 minus 7, that's 13. And so since this is 13, this would also be 13. Not too bad, I hope. Okay, so if you have 3 or more lines that intersect at a single point, so all of them are intersecting at the same point, it's called concurrent, or concurrent lines. And the point that they intersect is called the point of concurrency. I have a hard time saying that word. So the point of concurrency. If you're in a triangle, and you have 3 perpendicular bisectors, so we're bisecting, actually I should make these different lengths. So we're bisecting each side of the triangle. They're going to meet at a point of concurrency, and that's called a circumcenter, which can be inside or outside of the triangle, and I'll show you examples of that in a minute again. But so triangle has 3 sides, so it has 3 perpendicular bisectors, so they all intersect at a single point, and that's called a circumcenter. Okay, and there's a circumcenter theorem. Let me pause this. Okay, so you have the 3 perpendicular bisectors of the triangle. They intersect at a point that's called the circumcenter. And the circumcenter is equally distant to each of the corners, or the vertices, the vertices of the triangles. So in this particular triangle, our circumcenter is on the inside, which would make this length, and this length all the same. Okay, so regardless of where the circumcenter falls, it'll be this. If you draw a straight line from the circumcenter to the corner of a triangle, those lengths will all be the same.
And the other 3 are the same.
No. We don't know. Okay, so we know, let me highlight. We know that these 2 lengths are the same here and here. And these 2 lengths here and here are the same. And these 2 lengths here and here are the same. And then we know that these 3 are the same. With the circumcenter, we don't know anything about the ones that are still just black. They may or may not be the same. If this is an equilateral triangle, they'll be the same. If it's any other triangle, they're not the same. So we can't, unless we know for a fact that this is an equilateral triangle, we can't say anything about those. Does that make sense? Right, so we can be, depending on what type of triangle you have, the circumcenter will fall inside, outside, or on that side of the triangle. Okay, if you're in a cube triangle, you're inside. I'll just use the pen and not the eraser. Okay, and then this distance, and this distance will be the same. Because we go to each vertex. Okay. And it doesn't have to look like this where I'm touching the vertices. I can be in a cube triangle like this. I'm still a cube, right? Maybe not. That one's iffy. Hold on, let me try a better one. That's for sure cube. Perpendicular bisector goes here, let's say, and here, and I don't know, like here or something. So we're not going through the vertices, but it'll still be inside the circumcenter. And then the distances between here and the vertices will be the same. If you're obtuse, okay, these are the bisectors. There and there. So this line here is bisecting the longer side. This line and that line. And where circumcenter meets outside of the triangle. And that's okay, because if I draw lines to each of the vertices, those lines will all still be the same length. Not in my picture here because these aren't drawn proper bisectors, but you know, if it was drawn correctly, it would work. And if you're a right triangle, then your perpendicular bisector will lie on the hypotenuse. And you can see that it's already the same distance from these two vertices because it's bisecting that side. And then this distance here would be the same to that vertex. So depending on the kind of triangle you have, circumcenter can be inside, outside, or on the triangle. So this fact that the word center is in the name kind of makes it seem like it should be inside, but it's not necessarily. Bisector cuts an angle in half. So if you have an angle and you bisect it, you get two equal parts. Okay? And then our angle bisector theorem tells us okay, so basically, if I have an angle, and I bisect it, okay, so I bisected the angle, so this part is the same as that part, and I find some random point on the bisector, anywhere along the bisector. And this distance here and this distance here will be the same length. And they'll meet at 90-degree angles to be a distance, and those will be the same. Okay. Which, if you think about it, makes sense, right? If the angle's opening up and you go right down the middle of it, then the distance as you move up or down will be the same on each side because you cut it in half. And then going in the opposite direction, the converse tells us that if I have an angle and there's a point somewhere inside the angle, so in the interior, not out here on the exterior, and then these distances are the same, that means it's on the angle bisector. So if I were to draw a line through that point, it would bisect the angle. So same idea as before, where they both tell us kind of the same information. Basically, if these two angles are the same, these two lengths are the same. If these two lengths are the same, then these two angles are the same. So whichever one you know, like they give you, you can find the other with it. Does that make sense? So if I tell you the angles are the same, then you can find that these two lengths are the same or vice versa. Okay, so we have these example problems. Those are from the work packet. These markings tell me those distances are the same, which tells me that these two angles are the same. Does that say 58? Okay, so if this is 58, then this one is also 58. And then if you were told to find the whole thing, you just add them together. Here I have these two angles are both 19, which tells me that these two parts are equal. So 7x is equal to 2x plus 5. And then I can solve for x. Subtract 2x from both sides. 5x equals 5, so x equals 1. And so IU is 7x, so that's 7 times 1, which is just 7.
7 times 2 is 14 plus 5. I mean, 2, I forgot my okay, sorry.
Got it?
Yeah, I was confusing myself, but I got it.
Number 6, we have these two lengths are the same. That tells me these two angles are the same, so I set those equal to each other. 4x minus 1 is equal to 2x plus 5. Subtract 2x from both sides. 2x minus 1 is equal to 5. Plus 1.
Where are we at?
2x equals 6. We're on the same first page. So x is 3, and we want to find myw, so that's the 2x plus 5. So 2 times 3 plus 5 is 6 plus 5, so this is 11 degrees. So basically the same idea as with the angle bisectors, or the perpendicular bisectors and the angle bisectors are kind of the same idea, right? You get two parts that are equal to each other, so you can solve them that way. If you have the three angle bisectors in a triangle, they will always hit at a point, the concurrent lines, right? So I bisect each angle and I meet at a point called the incenter. Now the incenter will always be inside the triangle because I'm bisecting the angles, right? So I'm always inside the angle, which means I have to be inside the triangle. And the incenter is equidistant from each side of the triangle. So if we had the circumcenter were equidistant from the corners of the triangle, the incenter makes us equidistant from the sides. So this length, and this length will all be the same. Okay. So if we bisect the angles, these pieces are the same.